to select this. Okay, should work. Okay, let's get started. So, any question from this time? This time we finished talking about classical computation, and we finished with our introduction to classical complexity theory, where we talk about the NP-complete problems. They are the problems that are in NP and they are hardest in NP. So if you say can solve any one of those NP-complete problems, like 3 coloring or 3 set, you can solve everything in NP. And but also not everything in NP is NP-complete. For example, factoring. Well, we cannot really say it's not NP-complete, but it has not been shown to be NP-complete. Okay. And people believe that it's not NP-complete. Okay. And we are going to totally switch gears, so let's don't spend much time into this review. And if people don't have questions, let's switch into quantum computation finally. So now finally we are getting into quantum computation. And this is the model we are using. Using this quantum circuit model. This is also why we talk a lot about classical circuit model. Because we think quantum computation is done in the circuit model where you have wires, gates, and also measurement. So it's really like classical computation where you have wire and gates, but it's quantum. So if you want to get the classical information out, we only need to do this measurement and and then let's talk about element. Each wire now is quantum, so it's carrying 1 qubit of information. It's more than in classical. When it's classical, we have each wire carry 1 bit. Now it's 1 qubit. And well, we are pretty familiar with this qubit Hilbert space now. It's a 2-dimensional Hilbert space, and all the block sphere and the things. Okay. And well, 1 wire is 1 qubit, and we'll have n wires. So there are total n qubits here, so small n. And so the total Hilbert space, once again, is the tensor product of everything, because these qubits are going to interact with each other. So the total Hilbert space is the tensor product of all the qubits, so H1 tensor H2 tensor Hn. And the dimension is going to be the product of, so it's going to be 2 times 2 times 2, n times, so the total dimension is 2 to the n. And sometimes we also say, so the convention is we also say big N equal to 2 to the n. Okay? So that's the convention. And so those wires are where we hold the information. And once again, time flow from left and right. And we usually initialize the circuit in all zeros. Doesn't need to be, but the remater, so let's say initialize with all zeros. Okay. So time also goes this way, just like in classical. And the gates, okay. And the gates now are unitary operator. And the gate can, just like classical, they can have several wires passing through them. And so if 2 wires pass through this gate, then this gate is applying on those 2 qubits. And we don't have it, but we can also have 1 qubit gate. We'll see very soon. We can have 1 qubit gate where this gate only acts on this qubit. And as we said from very beginning, that all the quantum operation should be unitary. Quantum operation should be a unitary that map your state from a unit vector to another unit vector. So all those gates are unitary operator, and yeah, they apply on the wires that are passing through it on this picture. So, well, sometimes the picture is weird because if you draw this, then seems like you only pass through the neighbors, but that's just some drawing issue. You can also think about gates like, say the first qubit and the last qubit, but that's more about drawing issue. Okay, and there are measurement. Yeah, as we know, if you want to get classical information out of quantum system, you need to apply measurement. And before we talk about a lot about all different kinds of measurement, right? We say we can have like measurement in some basis, and measure in some operator, and generalized measurement. But here in this circuit model, is for simplicity of the notation, we say that all the measurement is just the simplest measurement, the measurement in computational basis. Okay. And usually they only apply on 1 qubit because, well, if you measure everything in computational basis, then it's same as you measure everything separately in computational basis. Okay. And yeah, so you will measure in computational basis and get a random bit. And this is okay because, as we also prove when we talk about measurement, that all the generalized measurement, so the most generalized measurement can be done with computational basis measurement, with some HR and CLA and weird unitary depend on the measurement you want to do, right? So in terms of computational power, this computational basis measurement is enough to do all kind of computation you want to do. So if you want to do a weird kind of measurement, you just need to add more and CLA qubit to your algorithm and do the unitary correspond to the measurement you want to do. Then you do computational basis measurement. Okay. So those are the 3 elements of our quantum circuit model. So wire, gate, measurement. Question? Okay, should make a lot of sense. Okay. And now there are things that's different from classical circuit model. So first, this thing, there is no fan out. So we also talked about this before. And so basically there are no fan out. You cannot split one wire into 2 wires and have like carry the same information. And this is just because of the non-cloning theorem that we have proven. So because if you want some state that you don't really know, split or state arbitrary state, split into 2 copies of the same state, and this is just not possible. Okay, we will prove this. And this is not possible, so your wire will have no fan out. And basically the number of wire will stay the same. Although sometimes people do a measurement and stop using that wire, but in general the number of wires stays the same. And also this is very easy to derive, but maybe you haven't thought about. That is, every gate is reversible. This is just come from that we say every gate is a unitary operator, right? Because from the basic of quantum mechanics, every gate must be a unitary operator. And unitary operators are just reversible. Remember from the definition of unitary operator, we have that U times U dagger equal to identity. And this U dagger here is just how you reverse your gate U. Remember, U dagger is another unitary. And we haven't said it, but it's possible to apply any unitary in a quantum computer. So if you apply a U, it's also possible to apply this U dagger operator. And yeah, because U times U dagger equal to identity, So if you just put a U dagger gate after your U dagger gate after your U gate, then that's same as you do nothing. So you can totally reverse your gate here. Okay. And that's different from classical computation, right? Because remember, classical computation, they are like AND gate. Wait, excuse me. Oh, I forgot to connect it. So classical computation, they are like AND gate and OR gate. And they are not reversible if you forgot their input, right? So AND gate, like you have, I forgot it. Okay, let's look at it up here. AND gate, where is it? Oh, we didn't draw a picture. Anyway. Okay. Okay, thank you. And the gate is like this, right? And anyway, so you lose some information when you compute the AND gate. So that you have one more. So say you have a 0 here and a question mark, you cannot reverse it because there are 3 different inputs that give you this 0 here. Okay. Okay. So, but in quantum computation, everything is reversible. So you need to think about when you want to do AND, then you need to keep track of the input to be able to reverse everything. That's interesting. And okay, so let's talk about the quantum gate. What are the quantum gates that we want to use? I guess any question about the basic principle should be fine. Okay. And okay, 1 qubit gate, and okay, so the first few things we are very familiar with, but now we give them pictures. So Hadamard gate, well, it's Hadamard, so we write it as this H symbol. Okay, and obviously it's 1 qubit gate. And just as a reminder, is this matrix. Hopefully you are maybe very familiar with it now. 1 square root 2, 1, 1, 1 minus 1. And it changed 0, 1 to plus and minus. And once again, you need to memorize them. This and the poly matrices, very important. And yeah, those very important poly matrices. Poly X, obviously is X, and its matrix form is this 0, 1, 1, 0. Poly Y is 0 minus I 0, and poly Z 1, 0, 0 minus 1. And okay, so but now we're in circuit model, so there's a little more we can talk about. And this X gate, you can think about it as a generalization of classical NOT gate, because well, it flip a single qubit, right? So if we act on computational basis, then it flip 0 to 1 and 1 to 0. And this is what the NOT gate do on classical bit. And you can see this is a very general thing. You can generalize any classical gate to a quantum gate by listing out how they act on computational basis and just linear extend them to the whole quantum space, right? Because every gate is unitary, and more importantly, every gate is a linear operator. So if you know how this operator acts on the computational basis, then you know the whole operator. Okay. And okay, so poly X is actually a classical NOT gate and generalized to quantum. Okay, so Hadamard, polys. And then there are the less well-known gates, so you better know them, but not hard required. So first of all, this is the phase gate. So the phase gate and this pi over gate are very similar because they are basically the square root of z and the square root of z. Yeah. So this phase gate is this 1, 1, 0, 0, I. And you see this I is the square root of -1. And I think we'll probably see later. You can think of this as okay, that's a little weird. But you can think of this as some kind of rotation around the axis. We'll see this interpretation later. Anyway, for now we can remember the matrix here. This S gate is matrix is this 1, 0, 0, I and the square root of z. And there is this T gate. Oh, sorry. And this phase gate, so it got two names. So we call it S here, but also sometimes people call it P because it's a phase gate. And there is this T gate, which is a square root of this 1i. So now it's this 1 and e to the I pi over 4. And it's also called pi over gate because there is an interpretation about this being a rotation on the axis, and the angle is actually pi over 8 instead of pi over 4. We might go maybe see that later. That's a more physical interpretation. Yeah. So those are single qubit gate. Should be very easy now. Just something you need to refresh your memory on. And then there are 2 qubit gate. Okay. And so first of them is C naught. I think we kind of see this, but now we yeah, we kind of see this when we talk about superdense coding and teleportation, but now we can see it in picture, and hopefully it makes more sense now. And there is a 2 qubit gate, so one qubit, second 2 qubit, and it's not symmetric between those 2 qubits. It has a control and a target. And if you write out its matrix, then it's this a lot of zeros and only 2 ones here and another ones here. And C naught stands for control naught, and control naught is a classical gate. Yeah. So C naught is really a quantum generalization of this classical control naught gate. And what we say is control naught because when you put it into computational basis, so say the A, B are computational basis here now, then this control qubit doesn't get changed because control qubit is used to control the target qubit. So this gate will just read this control qubit. Okay, this is A. And now if the A is 0, then it doesn't do anything to the second qubit. Right? So that's why it's controlled. And if it's 1, then you should apply this NOT gate. So we'll flip this B bit. And that basically change B to 1 minus B. Because you want to change 0 to 1, 1 to 0. And also you can write that as B XOR 1. Okay. We think about this carefully. This is B XOR 1 or B plus 1 mod 2. That also flip the B. Okay. And then we can write this whole thing. Actually, it's a little longer. Okay. Yeah, and we can write this whole thing now with this XOR notation. We can write this whole thing into a simpler form, right? So we can say C naught on these computational bases A and B. That's just A and tensor B O plus A. Because if A is 0, then it's plus 0 does nothing, and if it's 1, then it's same as this plus 1 here. Okay. Or define the whole action of C naught on every vector, because from this relationship you can write down basically its matrix here, right? Because so for every pair AB pair you can see the output, and those columns will correspond to this. So that's how you see you get this C naught matrix. And so now quick test. What's the C naught of plus and 0? Now anyone want to answer? Right. Final. Okay. So I guess let's do this example. So C naught plus and 0, and let's see how this linear extension work out. So we have C naught. Okay, let's be nice here and write down all the normalization. So this plus is 1 over square root 2, 0 plus 1, right? Let's don't write this here. So plus is this thing and 0 is 0. And let's just expand all this. So it's C naught of 1 over square root 2, 0, 0 plus 1, 0, right? And we say C naught is a linear operator. So we can pull out this 1 over square root 2 and have C naught apply on both of them. So C naught 0, 0 plus C naught 0, sorry, plus C naught 1, 0, parentheses, plus C naught 1, 0, and okay. Now it's C naught acting on a computational basis, so we can just read from here. And skip a little bit. So 1 over square root 2. So C naught 0, 0 because the control bit is 0. So it should do nothing on the second bit. Right? So it stays 0. So it's 0, 0. And then plus, then C naught 1, 0. The control bit is 1, so it should flip the second bit. Or it should be B plus A, 1 plus 0 is 1. So that's 1, 1. Okay, so that's the result. C naught plus 0 is 1 over square root 2, 0, 0 plus 1, 1. And it's beta 0, 0, if you remember our EPR state. Okay? So everyone okay with the computation? Okay. Then let's talk about other other 2-qubit gate. And well, this control thing, you see, we can really apply to all sort of different 1-qubit gate. So we can have a very general control unitary. That will be a 2-qubit gate. So you have So you have a gate look at this. So you have A, so it's control on the first qubit, and you apply U on the second qubit. So if you have a computational basis A here as input and some arbitrary state psi here on second qubit as input, then as we say, the gate don't do anything on control qubit, it stays A. And on the second qubit, if A is 0, then this whole gate does nothing, so it stays psi. And if A is 1, then we'll apply U, it's 1-qubit gate U on psi. Okay. So we can have this very general control unitary. And if you write down it as a matrix, you should look at this. When A is 0, then you will do this block of doing identity on B, and if A is 1, you will apply this unitary U. Okay. And if you write down this in formula, it is control U on A side, and it will stay A on here, and it's not very clear. Okay. And U to the, then we can write U to the A on side. So the U to the 0 power is identity, and U to the 1 power is U. Okay. And okay, so that's general, very general control U, but we have less general example of it is Control Z. It's also very useful. It's not as popular as Control Not, but it's also very popular, so it's got its special symbol. So Control Not, I should emphasize this. So Control Not will write it like this. So the control qubit is a dot, and the target qubit we write this kind of like an XOR symbol, right? It's O plus. And for Control Z, it also has a symmetric symbol that is actually both sides look the same. It's both of these solid dot here. And well, then you see that if you write like this, then you cannot see which one is the target qubit, which one is the control qubit. But that's okay, because if you write down this I in the U symbol, then you see that Control Z look like 1, 1, 1, minus 1, and this is actually symmetric between first qubit and second qubit. So that's a very nice property of Control Z. It is symmetric in the first and second qubit. Okay, and once again, it is symbol right like this. So like two target. That's Control Z. And then there is not control something qubit. There is this swap gate. It's not a control something, but obviously it's very useful. It swap whatever information on the first qubit and the second qubit. Okay. So so swap gate. If you write down the matrix, it's actually this, because you want to have 0, 0, stay 0, 0, and basically the thing do. So if you think about how swap gate act on the computational basis, so 0, 0 should stay 0, 0, but it should swap between 0, 1 and 1, 0, right? And that's what is happening in the middle. 0, 1 should swap between to 1, 0, and 1, 1 should stay 1, 1. And you can check that. So we just check on what the swap do on computational basis, but you can check. So this actually be homework. Swap on general gate, psi and phi will be phi and psi. If you have a product state here. Question on swap gate or Control Z and stuff. If not, then okay, so we have 1 qubit, 2 qubit, then we have multiple qubit, or actually it's 3 qubit. So 3 qubit gate, they are a bit too complicated. So actually there is only one of them that's famous enough for us to remember its name. That's a Toffoli gate. I think we also don't use it too much, but well, it's very nice. You still better remember its name, because people talk about a lot about it. And the Toffoli gate, what they do is very simple. It's basically, or it's just control, control not. So you can probably see the symbol here. So it has 2 control qubits. So this first qubit and second qubit are both control qubits. And the Toffoli gate won't do anything on it if you say our input is computational basis. And you apply a NOT gate on the third qubit if both the first qubit and the second qubit has input 1. Okay. So this A times B obviously equal to 1 only when A equal to 1 and B equal to 1. And once again, this O plus thing, if O plus 1, you will flip your C. So it's control, control not. You only apply a NOT gate on the third qubit if the first 2 qubits are both has input 1. And once again, that's how you do on computational basis. And you can do a linear generalization to all sort of input, even entangled input. And why is it famous enough to have a name? So first, this is something skipping the previous chapter, but this is universal for classical computation. And so that's very nice. So just like NAND is universal, but also it's reversible. So so remember, we said today that every quantum gate needs to be reversible. So it's universal for classical computation and reversible, so it's nice as a basis to build quantum computation, because then you can do every classical computation in quantum computer by doing a whole bunch of Toffoli gates, right? Because you can have Toffoli gates in quantum computer, and it's also universal for classical computation. So you can just build classical computation in quantum computer with Toffoli gates. And if you want to see more story about Toffoli gate, you can read chapter 3 of the book. Okay, so that's Toffoli, and that's basically the only multi-qubit gate we talk about. We give a name, and we back with other notation. Okay. So the notation of zero control. So say is compared to this, right? So we have control Z, we have control U. We always have a solid dot here. But if we have this, what should I say, this empty circle here, sorry, this hollow circle here, then it means it's control on zero. So you only apply U when the first qubit is zero instead of first qubit is one. And you can write down equivalence. That's saying as you flip the first qubit first, then apply this solid dot control, then flip it back. Okay? So that's just some notation you might see on the book or on paper. Okay. So any question about all the basic gates before we go into some example of quantum circuit? So, no? Then yeah. Then we go into quantum circuit. So those are things that you will see in your midterm final. So this is very important. You need to know how to do those computations. And we already see a really small example of doing C0, right? And but yeah, so those are kind of a thing that we'll do all the time throughout the whole class. This is how we write our quantum algorithms sometimes. So first example, so we have some circuit identity. First example is how we construct a swap gate. And the swap gate can be actually constructed out of 3 C0 gate. So if you place 3 C0 gate in this sequence, it's actually equal to our swap gate, which swap 0, 1 to 1, 0. So the first C0 has a target on the first qubit, has control on first qubit, target on second qubit, then you have this second C0, control on second qubit, target on first qubit, then last C0, control on first qubit, and target on last qubit. And we check this identity, so this is basically a classical computation. We check this identity on computational basis state. So we say input is A and B. Then let's check how this works. So A, B input, then on this state, then when the circuit calculated to here, it should become A and A plus B, AO plus B, just because the C0 formula we derived. Then on the second thing, then on this time slice, you should now the second qubit is the control, so you should stay A plus O plus B, and the first qubit should be AO plus this AO plus B. Okay. And well, this O plus is basically plus mod 2, so you can plus everything together, and A plus A is actually 0 because it's addition mod 2. So 1 plus 1 equal to 0. Sorry, 1 plus 1 equal to 2 equal to 0. and 0 plus 0 obviously equal to 0. So this A plus A is actually 0. So you just have 0, just have B left over. Then finally, so thus this time slice is equal to B and A O plus B. Then finally, on the last time slice, the first qubit is a control, so it's state B. And the second qubit become A plus B, then plus B. And we have the same calculation because the addition is associative, so you can calculate this B plus B first, then cancel out, then just say B and A. So yeah, so we prove that this circuit acted on computational basis is a swap. And so here we have the homework. To do that, we should say, you should prove that if gate exchange A and B on computational basis is actually swap on every product state. So if you have every product state input, you change psi phi to phi psi. Okay. Question about this actually very classical computation swap gate. Okay. Excuse me?
Mod 2, right?
Yeah, A plus A and mod 2. So everything is mod 2 here. Yeah. So A plus A mod 2, okay, you can think about A plus A mod 2. So everything is basically addition and it's mod 2. So A plus A mod 2 is equal to 2A mod 2. And 2 equals 0 mod 2. So, yeah. Okay. Mod 2 equal to 0. Oh, I shouldn't write so many mod 2. Let's see. The first one. Okay. Okay. Then we have also a very second example is also a very classical circuit. So it's copying classical information. So let's say you have some psi as input, then 0 on the second qubit, and then you apply a C naught here. And let's first see how this works on general state. So if your psi, let's say equal to A0 plus B1, okay. And this is, well, we have seen a specific example where it's a plus here, but here it is more general, so you have A0 plus B1, 0 here. Excuse me. Then, yeah, it's the same calculation. Then you expand this out, so it's A00 plus B11. Then you apply C naught on those 0, 0 and 1, 1. So C naught on 0, 0 stays 0, 0. And C naught on 1, 1, you will add this 1 on the second qubit, so it can become, on this 1, 0, so it add this 1 on 0, so it becomes 1, 1. Okay, question. And why do I say it's copy? Because it copies classical information. So if psi is computational basis state, so if psi is 0 or 1, then this becomes 0, 0 or 1, 1. So it's 2 copy of 0 or 2 copy of 1. But as we say, there is no cloning. So if psi is not just those two, so if psi is, say, the plus state, then it becomes 0, 0 plus 1, 1, and that's not same as the tensor product of plus state and plus state. Okay. And we have 1 minute. Can we finish this? Maybe. Okay, let's do this then break. Okay, then the last the third example, we'll just is another circuit identity where we show Z gate commute with the target of the control qubit of the C naught. Okay, so if you apply Z here, then apply a C naught like this, is same as apply C naught and apply Z. And we've seen this many times. So we only check how they work on computational basis state. Yeah. So if I input AB computational basis state, and remember Z is 1 minus 1. So how it works on the first circuit is on here it becomes minus 1 to the A and B, because it applies Z on the first qubit, right? So it should be have a minus 1 if A equal to 1 and do nothing when A equal to 0. So you can just write as minus 1 to the A. And so that's what this slide is. And then you apply C naught, so AB becomes A plus B, and the phase stay here. And if it's this circuit, then it basically go in different place. So AB apply C naught become A and A plus B. Then you apply Z gate on Z on the first qubit. Then you see that. Then you also get this minus 1 to A back. Okay. And before you have a break, you can think about, is it also true that if you apply Z on the second qubit, this is equal to this thing? Question mark. Okay, let's have a break. And wait. Oh, it's 20. sorry. Too early. Yeah. Okay, then let's do this. Sorry. It's on 20. So yeah. So let's see. Okay, I've done this. So let's try this. Okay, but we'll do this. Is this equal to Control then Z? Guess let's have a vote to keep people awake. How many people think they are equal? And how many people think they are not equal? Raise your hand. Okay, let's check. So this thing, okay, we can do this AB thing, right? AB. Okay, this is A and B here, and here it should be minus 1 to the B, AB, and the end it should be minus 1 to the B, and A plus B. Okay. And this thing, it should be after the C naught, it should be A plus B. And then you do this Z, and it should be minus 1 to the A plus B, and A plus B. So indeed they are different. Right? So we have 100% correct rate, although lots of people didn't answer. Yeah, because you see it's minus 1, one of them has B and one of them has A plus B, so different phase. And different phase actually different state, because or different phase actually give different gate, because this is just we are thinking these are the small part of the gate, and so this thing might have entangled to other things, so the phase here are actually important, right? because you have other part of the circuit and other gate that might be entangle everything and the things. Okay. So this is just an example to tell you be careful about when you apply this entity, the target gate and the control gate. Sorry, the target qubit and the control qubit are different. And then let's give other example, EPR. So now this is quite important or quite useful, because I will see very soon that this is what we do in super dense coding. And this create Epaperes, and actually you have seen this calculation quite a few times already today. So you start with 0, 0, and you apply headema on the first gate, then you apply a C0, then you will become this Epaperes at the end. And that's because you have 0, 0, then you apply headema once again, you will become this 0, 0 plus 1, 0 state. And we've seen this computation twice already today. The 0, 0 plus 1, 0 becomes 0, 0 plus 1, 1. And that's beta 0, 0. Okay? So that's how you create an Epaperes in a quantum circuit. There's a headema, then C0. And this is quite symmetric, so obviously you can have a header here, then flip this control target around. But anyway, you can create Epaperes like this. And then we can have, do we have time? Maybe. Then we can have super dense coding in a circuit model. Although it's a computation protocol, so it's a little weird to write it in the circuit model. But we can write it in a circuit model to make it more clear about what happened. Remember when in chapter 1 we do this in like text description, and it's a little weird, right? And hopefully it's easier for you to remember a picture. So a picture is this, and more reminder. So in super dense coding, what happened is it's a communication protocol. So it's Alice and Bob, and Alice is going to send one quantum qubit to Bob, and what she hoping to happen is she has some two classical bit A and B, and by saying this side to Bob should learn this A and B. Okay. So one quantum qubit to send two classical qubit, but a kind of cheat with pre-shared entanglement beta 0, 0. Okay. So the protocol start with Alice and Bob sharing this beta 0, 0 between them. And what happened is Alice is going to apply x to the b and z to the a. So basically apply x if b equal to 1, and then apply z if a equal to 1. And then Alice is going to send, so on this time slide, something you cannot see in circuit, but actually happen in communication model happen. That is, Alice is going to send her qubit to Bob. So from there on, both of these are Bob. Okay? And so Alice sent her qubit to Bob. And also, we have done so the calculation in chapter 1, I guess. So calculation we have done in previous chapter is that at this point, the state on these two qubits is going to be one of the 4 Biot bases. Sorry, one of the 4 Biot state based on what A and B here, and it will actually be beta AB. Okay? And I'm not going to write all the Biot states. You can refresh them, but they are looking like this. Let's talk about the circuit first. And yeah, so it's going to be one of the 4 Biot states, and then Bob is going to do a measurement in Biot basis. But in our circuit model, then we have, so we'll do the unitary transformation here. So in our circuit model, we only measure in computational basis, right? So we have those two measurements in computational basis. So we need to turn our Biot basis back to our computational basis, and we can check if this is correct, but not quite the revision is that you can see this circuit is just a reverse of the creation of EPR. And that makes sense, right? Because EPR pair is EPR creation, map the 0, state to the beta 0, and then you can reverse your C naught with another C naught, and reverse your header map with another header map, and that will turn beta 0 to 0, and you can check that you will map other beta to computational basis state also. Okay, so this thing and its reverse is quite useful. Is a transformation between the computational basis and the and the Bell basis. So I should okay. And we are on time to break, so let's do this. Let's take a break and finish this next class. Okay. Question? No. A, B here.对啊。
如果我想要的话，我是不是可以把 C 纳字写成 get 跟这样子相乘？
可以啊，
对，
只是这样子会很辛苦的。
可是
通常不推荐。
如果他后来像是这个例子，他如果写出来的话，我发现我没办法把它两个拆开来，因为
首先你这个写错，我不能这样写，我这边是假的那个，原空白的是那个空白 control 的意思，是要接起来。对。然后你写不出来嘛，那我们就要验算了。
就是因为
通常不推荐，因为很容易算错，太多了。所以你是算什么东西？
就是如果我先过 C not 的话，那我发现我之后要再对单一第二个 Q 币，我没办法把第二个 Q 币写出来，因为是不是就还是我？
你要把你因为你全部都写开嘛，那你这个 Z 你要写成那个4×4的东西嘛，你就要去算 identity Z 这样子。
对，可是因为它是不是可能会 entangle 还是怎样的？
没有，就可以照算啊。它是已经 entangle 的。但是我们现在要算什么东西 ？C not 的，等一下为什么还有 Z？我们现在要算什么？
然后你刚刚给的例子啊，就是先第二个 Q 币先 Z 在 C not 跟先 C not 再 Z 的话。
然后你是算在什么 input 的 state 上面？哦，你在算超级卷的哦，超级痛苦。
对啊，超级痛苦的。然后发现我没办法看出来第二个。
等一下，所以你的计算从哪里开始算？从这里开始算吗？
就是我可能写有点乱嘛，就是我假设左边这个的话，那我是不是就让它
干嘛？对啊，
然后它就是叫这边加一个符号嘛。
对啊，你不是在硬乘吗？对，加一个符号，对，它变这样子 ，OK。然后 C 纳这些东西
写出来这样子。然后右边这个我发现我不会算，就是比如说我先 C 纳的这个。
你不是也差不多算完了吗？所以你 C 纳特把它算到这样子吗？然后
我发现我不会算对它的逻辑，因为我只对第二个 Q 币做，我没办法。
对第二个 Q 币，那你就去看第二个 Q 币是0还是1嘛，然后是1的加符号，所以这里加符号，这里加符号，那就结束了。所以应该是我算对的吧？你这样通过的东西。对啊。
是，反正你说，因为只对第二个 Q 币做，可是我这个已经是它的那叫什么tensor起来的样子啦。
但是我其实不太懂。没有，不是，我们有 I tensor B， A B 吗？
对。
A tensor B。
对。
然后不是一开始就很久以前这个会是 I on A 跟 Z on B 吗？对。对啊，那就算 Z on B。
做这个就好了。
对啊。然后如果你要超级无敌痛苦的4×4的话，那你就去算这个 Z 这样。但是应该是一样的事情。但是尽量不推荐把4×4或者是话用8×8这写出来，
好像
就很辛苦。对啊，这样这种 computation basic 的算法会比较快。对啊，那这个 ZB 的话，那就是-1的 B4法嘛。对。
可是我有点不懂，一开始刚才有一个-1的，就是你过 Z 的时候写-1的 A， 那是什么意思？
就例如说这里会等于-1的 B 嘛，-1的 B4 方 B。 啊，这个是不是就是我们比较偷懒的写法嘛？那我们就不用写这个 case。
对。
这个因为我们知道这个是等于 b，if b 等于1，然后负 b，b 等于1。
哦，好。可是这样子是不是就是假设它只是 computational basis？
对，这样是假设它是 computational basis 的时候。
就因为不是很有可能它会是很多。
对啊，如果你这种 plus 的话，就没有什么负1的 plus 的事情了。
好。
对。
好，这样子。
拼错了。
之前在看 teleportation 那部分，有点怪怪。
teleportation
就是他最后不是要把 measurement 再送给 buff？
对啊，这个。
如果已经事先讲好说，我就是要用那个，就是用00这个 projector 去 measure 的话，那我一开始我就知道我就是要拿00的那个结果，那这样是我不用送。
你说拿00的 projector 是什么意思？这里不是
就 measurement 用00那个 projector， 它好像不是会出来，好像是00，然后第一个好像就是我们要的那个，然后还有01，还有B。
对啊。
那我直接拿00在 projector 就可以直接拿到第一个结果。
但是它不见得会是这个啊，你这个有点 post selection， 但是 quantum measurement 是随机的嘛，你不能决定说它就真的会吐这个给你，有点像说你 plus day 就是。
如果我用那个 projector， 不是就可以直接拿到？
对，应该是我
拿零零这个 projector 去弄这个。
对，但是这不是一个 complete 的事情啊，你要有 P00加的，就是 measurement 要有 completeness 的事情不是吗？所以可以有 P00、P01、P0、P1合起来这样是一个 complete 的 measurement 嘛？
这样吧。然
后你要那些 P、I、J 加起来要等于 identity 不是吗？所以不能说我就只量这个东西，你可以说我可以量是这个东西还是其他东西，但就是只有1/4的几率它会丢这个东西出来。
单一个这样不能成为一个。
是啊 ，measurement 是整组合起来，你要有这个 completeness 的事情。
这个，
虽然说有，好啊，不要看。P0不是一样，它这个 project 嘛，它只有1/4，就是这是个4 dimensional space， 你 project 到这个，它有4个 dimensional space， 你 project 到一个 dimension 啊，显然只有1/4嘛。
虽然是
Okay, let's get back. Okay. So let's once again talk about our. Wait, excuse me. What happened? Wait. Hello. Yeah. Once again, let's talk about these protocols involving Epaperes, and I think this is something you need to check because we don't have nice algebraic form for beta AB here. But you can check that if you put any A and B here, then you will get beta AB out. Okay? And here we only check one of them, so we have 0, 0 input and it will be beta 0, 0 as output. And you can check all 3 other things. And the reverse here will do a reverse. So here we basically check another pair. So we check A equal to 1 and B equal to 0. We are checking through the whole superdense coding here. So let's see how it happened. So if Alice want to send this 1, 0 bit string to Bob, and so what she will do is she will apply this x to a 0 because b equals 0 and z to the 1. So only thing Alice do is she apply a z on her qubit, and she apply a z on her qubit. So z 0, 0 plus 1, 1. So from now on we are getting lazy. Okay, so we are omitting all the normalizing factor because they are easy to add in. So omitting the 1 over square root 2. So we start with 0, 0 plus 1, 1. And we do z on the first qubit. So let's see while the z act on 0, 0. Or z on 0 doesn't do anything. So it's 0, 0, 0. Then z on 1, 1. And well, z on 1 give you a -1, so this becomes -1, 1. And now you see it's phasing doing something. So 0, 0 plus 1, 1 becomes 0, 0 minus 1, 1. So this is your beta 1, 0 here. Okay. And beta 1, 0 here. Then we see how it got reversed to your 1, 0. And then you apply your C0 gate here. And we see here. So C0, once again, C0 on 0, 0 is 0, and C on 1, 0. And this 1, flip this 1, so it becomes 1, 0. So it becomes 0, 0 minus 1, 0. And finally, you do a headma here. And well, headma you can actually apply, or you can do that too, but it's easier to see this as, we apply headma here. Okay, so it's easier to see this as this is, so both of them has second qubit 0, so actually it's 0 minus 1 tensor 0, so it's just the minus state tensor 0. Okay, so this point here you have minus state tensor 0. Then you do Handmark 10 is minus 1. So see it's 1 0 here, and when you do measurement, you have 100 probability you get 1 0 because this is a computational basis state. And you see that this circuit works. It when at least want to send 1 0, but will get 1 0. And obviously, you want to see if it totally works. You need to check all 4 different possibilities. And we are getting a little lazy here, and yeah, you can check that it also works for other pairs of A and B. So, question about this circuit representation of supertext coding? No? Okay, then supertext coding, obviously we followed it with teleportation. So this is how teleportation look like. So actually has 3 qubit. Oh, actually before this, so let's say something. So this kind of calculation, so how a quantum circuit, what's the result of a quantum circuit is very important. And we're going to have problems doing this. And one thing to remember, not so obvious, is that you can calculate everything in terms of like 2 to n times 2 to n matrices. So for example, a 2 qubit is going to be 4x4 matrix. Right? We also write down the C naught as a matrix here, although we didn't write down the top 3 as a matrix. So we have write down everything like Control Z as matrix, but it's better to not use C naught matrix in your computation. Okay, because well, there are just a lot of things to write down. Right, it's a 4x4 or even like 8x8 matrix. It's very hard, so it's better to do calculation like this. Maybe you expand all things in computational basis or other better basis, and do smart thing and see how C naught act on each element, etc. Okay. So yeah, although we define everything as a big matrix, when we talk about tensor product at the very beginning, we talk about it's just a space with a very large dimension. But remember, we also talk about things like when we talk about tensor product, we also have example. Remember, we also have this like a slot to slot thing, right? So we have like A tensor B acting on side tensor phi equal to A side tensor B phi, right? We have this relationship. I would say it's true. And yeah, you want to do this kind of thing instead of tensor everything out, because then you can do all the calculation on smaller space, and it will make your arithmetic a lot easier, and it save your time, and it will give you less mistakes. Yeah, so that's some trick you want to do this kind of thing, and try not to expand out everything in 2 to n times 2 to n. Okay. So that's a trick to remember. But obviously this is not like an SOP. So this is something you you need to build some example and be a little smart to do. Okay, then back to our main trick of discussing algorithms. So teleportation. Teleportation, there are 3 qubits. I guess we say we didn't multiply out everything, but we do basically multiply all our states. We just don't multiply out our gate. Okay. So write down the gate is very, very annoying. But state we kind of okay, it's only 2 to the n instead of 2 to the n squared. Anyway, teleportation. So there are 3 qubits, and as a reminder, so what we want to do is, let's also write this here. Okay. So what we want to do is Alice and Bob, and Alice has some state, wait. So Alice has some state. She doesn't even know what this state is. She has some state side here, and she wants to send it to Bob, but they only have classical communication, and let's say classical communication is double line, and Alice is going to send 2 qubits here, and we're looking down up here. So Alice is going to send, sorry, not 2 qubits, 2 classical bits, 2 classical bits, M1 and M2 to Bob, and they also pre-share some entanglement, and Bob is going to get this side at the end of the protocol. Okay. So as we said, at the start, Alice is holding this side that she doesn't even know it's arbitrary side, and she's sharing EPR pair with Bob. So it's beta 00 here. So the first 2 qubit is held by Alice, and the last qubit is held by Bob. And so what happened is going to be this. So Alice is going to be this measurement in Bell basis. As you already see, this is measurement in Bell basis. So C0 and Handmar, then measurement. And she is going to send a measurement result to Bob. And so like here, we use those double lines as classical wire. And this is actually quite standard notation. So if you are writing a quantum circuit, and sometimes we will do like adaptive things. So we'll do some measurement, and there are some classical data as the measurement result, and those classical data will use double wires, double lines to represent. And anyway, so there are double classical wires, and Alice is going to send those to Bob. So like maybe at like this point, things are on the Bob side, and Bob is going to do something on his qubit controlled on the classical wire. Okay, so that's something you can do. So I guess so the classical data is going to be random number. So I guess if you want to be really careful, we need to write down everything in density matrix. But that's very annoying, so we kind of deal with this in ensemble. Right? So we are going to enumerate case 1 by 1. Or we did enumerate case 1 by 1, like all the outcomes. And anyway, so Bob is going to control on the classical result and apply X gate or Z gate. So if M2 equal to 1, then Bob will apply X here. And if M1 equal to 1, then Bob is going to apply the Z gate here. Okay. And let's check some of the things here. And so let's calculate the first 3 steps of what is going to happen. So let's assume this psi equal to some A0 plus B1. And then we start omitting normalization once again. And so psi equal to A0 plus B1. So the actual starting state is psi tensor beta 00. So if psi tensor beta 00, once again, is 00 plus 1, 1. And we can just multiply everything out. That's A0, 0, 0, and A0, 1, 1, and B1, 0, 0, and B1, 1, 1. Okay. Nothing happens. And we do C0 here. Okay. And so the whole state here, then we do C0. So now you need to be careful, there are 3 things. So is control on first qubit, then target on second qubit. So we basically on CNOT on all 4 of those things. So control on 0 does nothing, control on 0 does nothing. So those 2 stay the same. Then control on 1, flip the 1 to 0 to 1. Control on 1 with 1 to 0. Okay. So become 1 1 0 and 1 0 1. Then thirdly, we do this head map. So head map, and head map change 0 to plus and 1 to minus. Okay. And okay, so 0 to plus, 1 to minus, and then we skip a step here, but we regroup everything. So we can write plus as 0 plus 1 and minus as 0 minus 1, and you group the first 2 qubits into 0 0 or into computational basis, so either 0 0 or 0 1 or 1 0 and 1 1. Okay, so the first qubit has those 4 possibilities that will correspond to n1 n2, right? And now the residual third qubit will have 4 different states. So as we say, you see either is A0 plus B1 or A1 plus B0 or A0 minus B1 and A1 minus B0. So those 4 states, not all of them are psi, but they are all very related to psi. You can see this A something plus B something structure, and actually something is either 0 1 or 1 0 or there is a minus sign. So when you measure this state on the first qubit, then you will project onto for one of the 4, right? So if the measurement result is 0 0, say, then that's only possible when your state is coming from this component, right? Because you measure 0 0, that's basically doing a projection onto 0 0, and all other things are also going onto this 0 0. So you are projected onto this component, and then your third qubit will collapse into this A0 plus B1, and that's exactly the psi state. And it will happen with 1 over 4 probability. You can check it out. So yeah, that's what happens when it's 0 0, and because your third state is exactly psi, so you don't need to do any correction. And let's just check other possibility. Let's say you measure 1 0 here, then your third state is, wait, why do I A0 plus B1? And then your third qubit is going to collapse into A0 minus B1. And you see, if you apply a Z gate here, then this minus sign will flip into a plus sign. And you will go back to your A0 plus B1. And that's exactly what happened, because you see you got a 1 0, then you will apply a Z gate. And yeah, so similar things will happen on 2 other bases. Sorry, other 2 cases. So that's how teleportation works. Okay. Okay. So any question on this circuit representation of teleportation? Once again, you want to check the details, check more of the calculation detail, you can read the previous lecture note. Okay, so that's the end of introduction to quantum circuit. And now let's talk something a little more theoretical. Okay, so quantum universality, and this is well, quite like classical universality. We want to have a small set of quantum gates that let you build any possible quantum computation, right? Like in classical universality, we have like say an AND gate and we want to compute every Boolean function. And so similar idea is quantum universality, but it's a bit trickier here, okay? Because so a universal quantum gate set is a set of quantum gates that you can construct. From this set of gates you can construct any unitary. But now there is a weird thing of approximately here, okay? Because the difference here is in classical, you want to construct Boolean functions, right? You want some function from 0, 1 to n to like 0, 1. But quantumly, the end result is a quantum state, and basically you want to construct a unitary. But you think about a set of unitary is something continuous, right? And it's not just not possible to. So the set of unitary is continuous, but the set of quantum circuits is something discrete, is something countable, right? Because you can basically count your circuit as positions and what gate you put in. So you will have something that's countable infinite to map into something uncountably infinite that's or something discrete, maybe into something continuous that's just not possible. Sorry, it's the reverse. So we want to map something continuous to something discrete, it's not possible. So what do we do is, for some of the set, you need to have approximation because it's continuous, so actually many of the unitary just look like each other, so maybe you don't need to construct the unitary exactly. Yeah. Okay, so that's something. Quantum universality, sometimes you only can get the approximation. Okay. And well, there are basically 3 sets of universal quantum gates that people want to think and use. And I think we will. Okay, yes. We. Okay, let's talk about this first. So 3 sets. Okay, so the first set is. Well, it's actually not a discrete set. It's actually a set that is infinite number. So it's C0 and all 1 qubit unitary. Okay. And you can prove that this is universal. And this is quite cool because, well, we limit all not 1 qubit unitary to just C0. Okay. And and something funny about this set is, well, I guess good and bad part. So the good part is this is exact set. That means it can approximate any unitary exactly. You can construct. You can construct any like n qubit unitary exactly from things in this set, but that's because this all 1 qubit unitary is also a continuous set, so there are uncountably infinite number of set gates in this, obviously. So okay, so the math check out, but this set is quite large. It's uncountably infinitely large. So that's a little annoying, but at least we cut our non-1 qubit gate to just a 2-qubit gate CNOT, and it's actually a pretty classical gate, as we said. Okay. And so that's like the first step. People get constructed a universal quantum gate set. Then we can simplify this to something easier. Thus, we can approximate the 1-qubit unitaries to just HEDMA and T-gate. And this is kind of why we talk about T-gate. So remember T-gate, let's see if I can do this. Okay, overshoot. But anyway, so T-gate is this gate. And its importance is a little hard to say here. But let's say it's not possible to do the universal with just HEDMA and X gate. So anyway, because T gate is a little, although it looks like just like a square root of something, but it has less symmetry, let's say. So then other case. So if you combine HEDMA with T gate, actually then you get an approximation to all single qubit gate. And I guess there is the story is kind of the thing we didn't say here. So the story here is kind of what about the other way around? So why we didn't have the universal gate set with say HEDMA with poly X, and that's because, or like HEDMA and poly Y, and that's because HEDMA with say poly X has too many symmetry, and then if you just have a whole bunch of HEDMA and X and HEDMA etc., then let's say you have this thing, and it's actually inside something called Clifford group, right? And means if you just combine HEDMA and H, then it will basically only turn into HEDMA and poly. So let's say HEDMA X and HEDMA, and that's only equal to Z, right? And you know HEDMA square equal to identity, and A square equal to identity. And yeah, so if you just have HEDMA and X, then basically the only thing you can get is HEDMA or X or Z, or HEDMA X. Yeah. So anyway, so if you pick your two gate with too much symmetry, like HEDMA X, like HEDMA and poly, or HEDMA, even HEDMA and S, then you are all the combinations stuck in the group called Clifford group, and then it's a discrete set, and you will not get approximation to all single qubit gate. But what we do is we pick HEDMA and T, and T is weird enough such that if you just place your HEDMA and T in weird orders, so say like HEDMA T, HEDMA T, T, HEDMA, T, HEDMA, something like that. These kind of things. And actually those sort of string is actually able to approximate any single qubit gate. Yeah. And we'll probably, so there is a sketch of a proof that this is possible in a book, and we'll not talk about it right now, and actually the proof is a little annoying, so we'll probably also skip that later. So if you really want to see this, you can look up the book. But anyway, the bottom line is Hedema and T, you can use them to approximate any 1-qubit unitary. And because this approximates this, and we know this is a universal gate set, so CNOT, Hedema, and T is also universal. Although now it's approximately universal, because now you actually have a discrete thing. And this Hedema and T become, or 1-qubit unitary is an approximation. And this is I would say, the most standard universal quantum gate set people think about, but obviously there are other gate sets. and there are a lot of theory built around this, because obviously if you want to think about stereo quantum computation, first thing you want to think about is how to construct every possible computation. And there's a very famous theorem on this, that is so this Hedema and T approximating 1-qubit unitary, the approximation is actually very efficient. I should say, okay, efficient means efficient in the error of approximation. I think it's polylog. And efficient means, I should say here, right? So it's a polylog in one very epsilon. And this efficient approximation is discovered by two actually physicists, I believe, Solovey and Kitaev. Solovey, Kitaev theorem. And just like we say, it says Hedema and T can approximate any single qubit gate to error epsilon. We didn't define error, but is some kind of distance between two unitary or two matrices, and it's to polylog one very epsilon error. Yeah. And yeah, this is something very cool on a theoretical perspective, and I think even right now people are still trying to improve this, and there are many extensions on this. Say, how about we change this set to other thing? And it turns out, although we spend a lot of time saying Hedema and X doesn't work, but actually things that doesn't work is in minority, because you need a very high symmetry for this to not work. And basically, if you just pick two random things here, and you can build some kind of Solovey-Kitaev to approximate everything in 1-qubit. And because, okay, that's going to a little sideway. So because you can think about your Bloch sphere, right? Your 1-qubit is a Bloch sphere. And well, unitary is like two rotations. Let's say one of them is the axis. So you think about, so one unitary is a rotation on your Bloch sphere, so it's a rotation about some axis in some angle, and another unitary is another rotation in another angle. And just think about you combine arbitrary sequence of those two rotations. And if your angles are not in some weird symmetry, then basically you can do those two, combine those two rotations into any kind of rotation. Because you keep combining them, and they always give you something different, and if you do enough of them, you will cover everything possible. Kind of like if you keep adding irrational number, you will fill all real lines. Okay, so that's very rough intuition. And let's go back from our digression one level. So that's one thing you can change on solo key off. You can think about your change the state. And maybe more practical thing is excuse me. So that's different case set, and maybe more practical thing is just change this polylog to some smaller poly, and you can prove that the smallest possible thing you can do is linear poly. Is a linear log, so log 1 very strong, and I believe people are achieving this. Yeah. So there are work done recently showing that you can do do this approximation in only linear log 1 very strong. And there are other more finer detail you can generalize this. So level key type theorem, and that's quite interesting. Okay, and so that's a universal case set. But so let's go back from our digression main level, and the bottom line is C naught Hedema and T. If you just place those on your circuit, you can do any quantum computation. Okay, and it's proven. Question? Okay. And if not, and there are another pretty popular set of universal quantum gate set, although it's not really universal. It's this Toffoli and Hedema. Okay. And remember, Toffoli and Hedema, Toffoli is this control knot. And well, first is not really universal, because if you look at the matrix elements of these things, this is a real matrix, and this is classical, so it's also a real matrix. So actually they only approximate real unitary. Okay? But it's still universal computation, because if you want to do a complex unitary, let's say there's a complex unitary you want to do U, then you can write it in its real part and imaginary part, although they are non-unitary, but you can do this decomposition and actually use the Hedema and Toffoli to do some real computation, and you can get the measurement outcome. You can get the same measurement outcome probability as the unitary you want to do. So it's still universal in computation power, even though you only do real unitary. And so that's Toffoli and Hedema, and people also use this in research because, well, it's pretty cool, right? It's kind of separate into the classical part and quantum part, because you know the Toffoli is universal in classical computation, and it's kind of, you do classical computation and then you add in some quantum part. Okay? So that's pretty cool. And maybe I should. Okay. And any question? We have 10 more minutes. Okay, so we cannot finish this, but then we switch into another topic. That's now we are getting quite theoretical. It's like a complexity theory. It's a complexity theory that we kind of skipped when we talk about classical computation. That is this Oracle model. Okay. Well, so let's talk about this very theoretical thing of quantum oracle. So the motivation is like you have some sub-algorithm, okay? So let's say your algorithm has some sub-algorithm that you want to run many times. And the last sub-algorithm is compute some classical function, f of x, okay? Because you are solving some partial problem, probably. So there is some classical function f of x, and it's a sub-algorithm, you can compute it. And we'll see later that sometimes we think these are the input. But for now, let's think about this is some sub-algorithm, and it takes some time to compute. And now we want to put this sub-algorithm kind of like a black box in our algorithm. And now we think about what happened when we compute this f of x in a quantum computer. Okay? And it will be this unitary here that's related to this f. So it's called u of f because the unitary related to f. And then you will have an input part and record part. So input has x here. So you will have some qubit that you want to put x here, and you only read the input and it will still output the x here. And there is a record register y. So this y is, well, for now you can think about y is like 0, although you will later see that you can do something funny here. So there's some record register that might start with something y, but the important thing here is it will write down this f of x here. Okay, and here we are doing this a little fuzzy, but let's say f of x is 1 bit output, so this O plus is just plasma 2. And the important thing here is we do this O plasma 2 here, so it has this weird form of output being x and y O plus f of x, because u of x must be reversible. Right? It needs to be a unitary. Let's compare this to classical oracle. So if you want to have an oracle in classical computation, then you can just have input x and you output f of x. Right? No, it's okay. If you have some sub-algorithm, then you can do this thing. And but that's not good for quantum because you want everything to be reversible. And yeah, you want to reversible, then this thing make more sense. And in terms of algebraic, that is, you have UF apply on computational basis xy, then it become x and yo plus f of x. Okay. And yeah, you can check that is O plus make it reversible. Okay. And well, then what's quantum about this? What's quantum here is now interesting happen is you can compute this f of x in superposition. Let's say now this input x here you don't do computational basis state. So this x you actually put plus state here is 0. Then the state here will be I write this wrong. Okay, so it's 1 0. Okay, so this plus is 0 plus 1. So state here is 0 0 plus 1 0. And we can see this computer so what is computer in superposition mean is the output state will become, well, now we can do this computation here. So 0 0 becomes 0 and 0 plus f of x, f of 0. So that's just f of 0 here. And 1 0 become 1. And y is still 0 and it's just f of 1. Okay. So you see that you have this entangled superposition of f of 0 and f of 1 both getting computed. Okay? And I guess this ability to do computation in superposition is one way to see where the power of quantum computation comes from. Okay. Is quantum superposition. We'll see later, or maybe just not next Monday. We'll see that this give you ability to get quantum speed up. We are going to do something that's not quite possible classically. And as we said, we basically restrict f of x to a Boolean function. Although this is not true at the end of this PDF, but most of the time it's a Boolean function. And for now, let's assume it's a Boolean function. So the second register is just 1 qubit, 0 or 1. But you can imagine that obviously you can also extend this to many qubits. Although then it's plus, you need to pick something that's reversible. Okay. For now, let's say it's a Boolean function, and your f of x. Once again, Boolean function has some n-bit input to 1-bit output. So if we write down the thing actually in those lines, you write it out, then you have this UF as n-bit input x here and then 1-bit output y here. Output and this output x and the y plus f of x. And the notation we didn't say here, so sometimes we'll use this thing. So a line and a slash, this means multiple qubit. Okay? Just the notation. And more notations. So there are many names for this UF, and it's called the oracle. And it's also called a query, and it's also called a black box. I think for those things, black box probably make more sense, right? It's something you can look at. So it's a box that's totally black and it do something you don't really know. Right? So it's like a sub-algorithm that you don't look into its code. So it's just a box and it will do something. And it's oracle. It's also called oracle because you think it's like giving an answer from the God. So it's just something you pay to get the answer from the God. Okay? And yeah, that's the idea. Oracle is something costly. You will pay to put it into your circuit, and you will compute one answer for you. And from this oracle, also from get and then query. Query is basically a verb, but you also use it as a noun. So it's something you can query the oracle to get your answer. And yeah, just as we said, query is actually a verb. So people will say you query oracle. Basically means put this in your circuit and pay the computational cost, and you will get one copy of the answer out. Okay. And now this is something tricky that we'll talk more about later, and it's a bit confusing. Hopefully you can say here. We also think this oracle as an input. Okay. So now we have two input. And let's first say how we think this as input. Because we can list all the truth table of this f of x, right? So there are 2 to the n possible input to this f of x. And we can list them as a bit string. So f1, f2, f3 to f2 to the n. And this truth table of f can be think of the bit string. And we can think this bit string as the input to other problem that we want to solve. So we think this f as a sub-algorithm, then there is some other thing you want to compute on the output of this sub-algorithm. that we don't have time to go into, but next class we will see. But so the very confusing thing here is there are 2 inputs. So I don't have a good way to distinguish them, but I just need to not confuse them. So there's one input that is input to this f of x, that is x, and also this whole truth table of f as the input to your autoalgorithm. Okay. So that's confusing, but hopefully you don't confuse them too much. And those 2 inputs have different sizes. So this is a big and big string. So this truth table of f is big and bit, and remember this f is 0, 1 to n. Let's just say f of x. This is f of x. X is a small and big string, and yeah, just don't confuse those 2 inputs. There is a small and big string, and there is a big and big string. That's a truth table of all possible f of x. Okay, so we are slightly over time. Any question? Or we'll talk about query algorithms next time. Okay, see you next time.等一下，我先。